my Visual Python project, I created a demonstration of conservation laws and projectile motion through a golf swing simulation. The simulation treats the collision between the ball and the club as an elastic collision, and it assumes a circular club path, which is not reflective of an actual golf swing. So I start by creating a fairway, ball, and a club. Fairway is just a box with these dimensions, which I established in meters. The ball, I gave it a position, and I gave it a radius, which the radius actually is just the real radius of a golf ball magnified by 50 for visibility. I gave the ball the mass of a real golf ball, and I established the cylinder's position relative to the ball's, or the sphere's position, so the club's position relative to the ball. I wanted the club to start left of the ball, so I just subtracted from -90 the width of the club and the radius of the ball. And then I gave the club a mass of 0.2, which can be changed, as we will see later. Here I'm also defining a ball speed multiple. Since it's using a circular club path and energy conservation to determine the speed, the speed generated by the club is not reflective of an actual golf swing, so I have to multiply it by a multiple of 4.5 to get a realistic ball flight. And I'm also establishing a launch angle, which we'll come back to. Here I'm establishing a gravity vector, and then I'm saying time equal to 0, delta time, which is how much time passes through a loop, setting that to 0.01. And then here I'm defining the angle which the golf club is at. Given the position, that's the position of the golf ball at the beginning of the golf club, excuse me, at the beginning of the swing. At the beginning of the swing, potential energy and kinetic energy are both 0. So here I'm starting the first loop, which is the backswing. I'm setting the rate to 100 to get real time, and I am utilizing real time and utilizing DT to rotate the club. So I want the angle to ultimately go from 3 pi over 2 to pi over 2, and I am rotating it across the z-axis, because that is what will cause a circular rotation relative to the viewer. And I'm rotating it at an angle for every time it goes through the loop. It's rotating by an angle of minus dt over pi. So while t is less than or equal to 1, that means it'll go through 100 times, and 100 times 0.01 times 100 is 1. So by the end, it will have rotated minus pi, which is what I'm looking for. And you have to rotate it about an origin. So I just did the top of the club, plus I considered like the average arm length of a person, magnified by 5x, just to get a more realistic looking swing. And here I'm establishing, I'm calculating potential energy as the club moves up. So potential energy is work, which is mass times gravity times height, or mgh. And so club dot position is calculating the position of the center of the golf club. So I did club times club dot m, so the mass of the club, times g, and then to find the height, you have to add the position of y, which once again is at the center of the club, the y position, plus you have to set up a triangle to find the rest of the y position of the club. So that's just some simple trig right there. And then I'm updating time. So once that loop ends, it should be at the top of the backswing. And where potential energy is greatest, so I set potential energy max to the potential energy at that moment, and I'm printing it. And so the next loop is going to be the downswing, which is essentially the same thing, same code as the backswing. I just changed the sign, so instead the angle increases, so it rotates down relative to the viewer. And I'm also calculating kinetic energy at this point by subtracting the max potential energy, which was at the top, from the current potential energy. And yeah, so I'm going to print the potential energy once the loop is ended. And so at the bottom of the downswing, you're going to calculate the club head speed there. Given energy given the formula, kinetic energy is equal to half mass times velocity squared. To find the velocity, get the square root of 2 times kinetic energy divided by the mass. So that's calculating the club head speed. So I'm printing that, and then I'm calculating the momentum of the club. When momentum is just mass times velocity. So, as I mentioned earlier, I'm assuming that the collision between the golf ball and the club is an elastic collision. So this means that momentum and kinetic energy will be conserved. So you can solve a system of equations to determine the ball speed. So it's simple, you can just plug it into ball from alpha, but to solve it independent of the specific values. So looking up here, if I wanted to change the mass of the club, for example, you have to set up a general system of equations and then isolate x, and you're kind of left with a complicated quadratic equation in standard form with a lot of variables, and but most of them they're all constants except for a, and they're constants that have been defined earlier in the program. So what I did was I defined a function at the bottom, which can be called at any time. I called it QR for quadratic, and so the standard form of a quadratic equation is a squared plus bx plus c. So I took those as parameters, which I got from the isolating x in the system of equations above. And so here's this quadratic formula, the discriminant and then the 2 solutions, and I return the positive solutions, or otherwise I print that there are no positive solutions. So using that quadratic function that I defined at the bottom and the math of energy conservation in that system of equations, I plug in what I calculated for A, B, and C, which was all constants that I defined earlier in the program. I plugged that in and I set that equal to the ball speed, which gives you the ball speed, and then I multiplied it by the ball speed multiple that I defined earlier. So this provides a more realistic ball speed, which will lead to a more realistic flight of the ball in the air, so more realistic projectile motion. So then I established the momentum of the ball, which is very important for the code of the projectile motion. So the momentum is mass times velocity. So we have the velocity and the mass, but as we're doing projectile motion, you have to get the components of the velocity. So you multiply by the vector quantity with x being the cosine of the launch angle, which we defined above, and y being the sine of the launch angle. So that'll give you an accurate vector quantity for momentum. And then I'm setting time equals 0, again, just so we can get an accurate perception of the time the ball's in the air. And so we're heading to the last loop here. So this one's going to be the follow through and the projectile motion of the ball. So while the y position of the ball is greater than or equal to 1.27, and that number just comes from right here, the y position of the ball initially. So while that is true, once again setting it to real time, I do an if statement to kind of isolate the motion of the club from the motion of the ball, and I just utilize the same code as I did for the backswing and the downswing. This time just increasing the angle until pi over 2, which will get us to the same position as the top of the backswing, just the other way around. And then I established the net force as just a vector, just net force is gravity, mg, because in projectile motion, if you're neglecting or not looking at wind resistance, gravity is the only force. Thus, the momentum of the ball is going to be the current momentum of the ball plus the net force times delta time. And then the position of the ball is going to be the current position plus the momentum divided by the mass times delta time. And then I'm updating time. And so after the loop is over, so once the ball has landed on the ground, I calculate distance, which is just the initial, the current position of the ball, the position of the ball after it hits the ground, plus 90 because the initial action position was negative 90. And I find the max height time because using projectile motion equations, when the y velocity is 0, you get the max height time. So that's a simple calculation. And then plug in time into projectile motion equation for y, and then you get the max height. And so I print out the time, the distance, and then max height, and ball speed, and the launch angle, just to give a sense of the entire flight. So now I'm going to briefly show how the simulation works. So I'm going to run it. So I have it set up the mass of 0.2 right now, and launch angle of 0.25. So this is going to be a ball flight of kind of like a typical kind of amateur golfer driver swing. So let's take a look. It's the backswing, the downswing, follow through, and projectile motion. So the ball traveled 173 meters, which sounds about right for a typical amateur golfer driver swing. Its max height was 11 meters. The ball speed was 61 meters per second, and the launch angle was 0.25 radians. So now I'm going to do a simulation of maybe an amateur golfer who can't hit, or a kind of a beginner golfer who can't really hit the ball, get the club face square, so they're going to hit the ball lower, and you're going to see that the distance dramatically decreases. So yeah, when I hit the ball at the bottom of the club face, and the ball only travels 75 meters, the max height of 1 meter. And then maybe a professional, so they're going to get a higher launch angle with their driver, or simulate more ball speed. So set the launch angle to 0.3. And look at that ball flight. Much further than before. Traveled 215 meters, so maybe a professional hit a little further than that. So you could adjust the multiple would be different for professionals because they generate much more speed than an average golfer. But yeah, so that is my golf swing Visual Python simulation.